Okay, now I'm going to talk about perhaps the most important conceptual um, issue in all of statistics. Um, it's called the central limit theorem. I'm not going to write those words down anywhere in the video, but um, this theorem is central to um, the the bulk of statistics and what we use statistics for. Um, Now, to introduce the whole idea, we need to make sure that we understand the difference between these symbols. And these symbols are used throughout statistics. Um, and you're probably familiar with mu and x bar. They both mean mean, but mu is the mean of one thing, and x bar is the mean of something else. Mu is to sigma as x bar is to lowercase s. Those are both standard deviations. And remember, standard deviation is a unit of unusualness, like a centimeter is a unit of length, or a kilogram is a unit of mass, etc. A standard deviation is a unit of unusualness. Now, mu and sigma, those are the mean and standard deviation, respectively, of a population, whereas x bar and lowercase s are the mean and standard deviation of a sample. And it works out nicely that what these two guys are called is a little bit of alliteration with population. These are population parameters. These two guys are called parameters, and these two guys are called sample statistics. And the whole idea of the science of statistics is to use statistics to make inferences about parameters. That's, in a nutshell, what the science of statistics does. Okay, so let's take a look at what we're dealing with here. Suppose you have a population, and you take a sample from that population. Say you take some measurements, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and then you take the mean of those 10 measurements, and you stick that over here. It looks like it might be, I don't know, about here, x bar. All right, now, then you take another 10 measurements. Let's see, that's 10. And this x bar might be here. And you could keep on going, 10 more measurements. That's the last one I do. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that's another x bar. Now, you can theoretically keep on doing that over and over and over. Each of these x bars is a mean of a sample of 10 measurements from the population. Now, what I'm going to show you in a second here is a theoretical distribution of infinitely many x bars. Each one of these x bars represents a sample of some size. In this particular case, I was doing 10. Each one of these means, each one of these x bars is the mean of a sample of some particular size. Okay, so that's going to explain what we're going to be looking at on the next page here. And I'm going to pause, make sure I have it set up. Okay, so we have this distribution of these x bar guys, sample means. Each one is a mean. Each one of these represents an entire sample of a certain size. So we call this distribution a sampling distribution. It is a distribution of sample means. Later on, you'll realize that you can have a distribution of sample proportions. But in this case, we're dealing with sample means. And one of the important aspects of the central limit theorem, it says that if you have a distribution of sample means like this, then if the samples are large enough, then the sampling distribution will have a normal normal shape, a bell shape, even if the original population didn't. Now, if the original population is normally distributed, then the sampling distribution will be normally distributed even with small samples. But something else that the central limit theorem says is that the mean, this is the mean of the sampling distribution, the mean of the sample means, will be equal to the mean of the population that the samples were taken from. Now, if you think about it, if we take samples over and over and over, those sample means, in the long run, since each of those samples came from this population that has a mean, it kind of makes sense, if you think about it, that the mean of all these sample means would be the same as the mean of the population. And that's something that the central limit theorem says. Now, each of these sample means, remember what statistics does? Statistics, the science, is the science of using sample statistics to make inferences about population parameters. Well, each one of these, a sample mean is an estimate. Formally, it's called a point estimate. A sample mean is an estimate of a population mean. So it's an estimate of the population mean. And every estimate is going to have an error. This right here is the error of the point estimate. And how would that be calculated? Well, like the deviation, this is just going to be x bar minus this mu sub x bar. That's kind of sloppy. But it's this measurement, this point estimate, this sample mean minus the mean of the sample means. That's the error. Now, just like we had in the population distribution, we had a standard deviation. Well, we have the same thing in a sampling distribution. The only difference is you don't call it a standard deviation, you call it a standard error. It's the average of all of these errors. Just like the standard deviation is the average of all deviations. And so, just like with the population distribution, we can calculate how unusual a particular estimate is under the assumption that we know the population mean by using a z-score. Or in certain cases, if the samples are small, you'll learn that you use a student's t distribution instead of the z distribution for small samples. So what we're calculating here again is a z or a t score for a sample mean, and the calculation is basically the same. You take the error, which is this, it's the sample mean minus the mean of the sample means. That difference, how many standard errors are there in this error? So we divide by the standard error, which is, like the standard deviation, a unit of unusualness. So we have found the measure of unusualness as a t or a z. It's typically called a test statistic. A test statistic. How unusual is our sample mean? It's called a test statistic. Okay, so now the big thing is, what in the world? How do you calculate? We know from the central limit theorem that this mean of the sample means is the same as the mean of the population. But we don't know what this this standard error is. So let's go back to this page here, and let's suppose we're talking about, for example, let's suppose we're talking about IQ, which has approximately, I'm just going to roughly, approximately the mean is 100, and the standard deviation is approximately 15. Okay, so that would put an IQ of 100 will be right here, and each of these notches is one standard deviation. And this would be an IQ of 85, this would be an IQ of 70, an IQ of 55, an IQ of 145, and of course, the higher your IQ, the more unusual that occurrence is. And that shows in the fact that there are fewer people with very high IQs, just like there are very few people with very low IQs. There are relatively many people with the typical IQs around the average. Now, if we take consider these sample means over here, where each one of them is the mean of a sample, would the sample means since each one of these represents the mean of a sample of a certain size, what would happen if, remember what I'm dealing with here is that standard error. I'm trying to recall that standard error. We want to figure out how is that standard error. The standard error is not the same as the standard deviation right here. It's not the same. These sample means, since they're the average of 10 or however many IQs in this case, won't the average of 10 IQs be closer to the mean IQ, closer to 100, than the individual IQs are? Because the ones on the positive side, on the high side, and the ones on the low side will kind of cancel each other out. So these averages or means will tend to be closer to 100 than the individual IQs because they're averages. And the way it actually ends up working is that that standard error ends up being the standard deviation divided by the square root of the sample size. So that if we took a samples of 25, suppose the samples were 25, then the standard deviation we said was 15, and the square root of 25 would be 5. So we'd have 15 divided by 3, or 5. So the standard error, the mean here, would still be 100, but we have a standard error of only 3, of only 5. Oh, 15 divided by 5 is 3. So 103, 106, 97, 94. So in other words, if taking a sample of 25, a sample of 25 people having a sample mean of 106, that would be 2 degrees of unusualness. T would equal 2 degrees of unusualness. That would be just as unusual to find a sample of 25 with a mean IQ of 106. That will be equally unusual as one person with an IQ of 130. They're both 2 degrees of unusualness above the mean. And this formula here is going to be the key to calculating test statistics. And the larger the sample size, it should make sense that the larger the sample size, the closer these sample means will tend to be to the 100. If you take samples of 100, then you'd have 15 divided by the square root of 100, which would be 10. So if we take samples of 25, would look like this. Let's say in another color, I'll do blue. Let's say we take samples of 100, then that will be 15 divided by the square root of 100, which is 10. That will be 1.5. So we'd have 101.5, 103. Taking a sample of finding a sample of 100 IQs with a mean of 103 would be just equally unusual as a sample of 25 with a mean of 106. I hope that clarifies what a sampling distribution is and how the central limit theorem works.